So continuing a discussion on bivariate data, we're going to talk about correlation. And first we can look at a graph like this. Which graph has stronger form? The direction on both of them is positive, but which graph would you say has stronger form? The top one or the bottom one? Sometimes the eyes can be deceiving. A closer look, especially at the scales on the two graphs, reveals that they're actually the same graph, just zoomed in differently. So you can see the points are the same down here. It's just scaled a little bit differently. And so our eyes can be deceiving on the strength of the graph or of the correlation. And so we've got a formula that can help us quantify that relationship. R equals 1 over n minus 1 times the sum of x1 minus x bar over s of x times y1 minus, or yi minus y bar over s of y. That's not really as bad as it looks. That parenthesis is the standardized value for the x's. That's the standardized value for the y's. You're going to multiply those together and then add them up. And then that n minus 1 business is similar to what we used with standard deviation. That's the degrees of freedom. So after we get that sum, we multiply it by 1 over n minus 1 to obtain correlation, R. So let's look at a problem. I found this one in a Brays and Brays textbook. They examined 5 small towns in South Carolina and asked the towns, the individuals are the towns, and they said, hey, you town, what percent of your population that's over 25 years of age has 4 more years of college? And furthermore, what's the per capita income in thousands of dollars? And they got this data set right here. So it was Greenwood and Hilton Head Island and Myrtle Beach, Orangeburg, and Sumter are the 5 cities. Again, this is the percentage of people who were 25 and over that had 4 or more years of college, and this is the per capita income in thousands of dollars for that community. Type these into your calculator, and let's see if you can do correlation. Pause the video, give it a shot. So now I'll walk you through it. I've typed the data into my calculator, and I'll walk you through the process of what we should do. The first thing I want to do, even though it wasn't explicitly asked, is I want to make a scatter plot of the data and see what it looks like. So I go to my stat plots. I make the first one a scatter plot of L1 against L2, and I hit zoom 9 to graph it. So there's my data set. And so I could talk about the direction is generally positive. It's not terribly strong. It might be linear. This point seems to lie outside the pattern a little bit. And with such a small data set, it's kind of difficult to get a great feel for the data. But I still want to graph it nonetheless. And now I'm going to go and use the formula that I did before. I'll rewrite it here for us. So it's R is 1 over n minus 1 times the sum of x minus x bar over s of x, y minus y bar over s of y. And so in my lists, I'm going to put this in L3 and this in L4, but I notice I need x bar and s of x. So before I continue, I want to press Stat, Calc, toVar Stats, enter. It says L1 and L2. That's great. If you were using an older TI-83 or 83 Plus calculator, you wouldn't have this menu, but it would default to using L1 and L2 unless you told it otherwise. So hit enter a couple of times and I get this summary data. The down arrow shows me there's some more down here, including the mean of y and the standard deviation for y. Now what I want to do in my L3 is to put this information here. And so the way that'll look is it'll be L1 minus x bar over s of x. That's what's going to be in L3. So again, in L3, It's L1 minus X bar, which is vars statistics number 2, and then the S of X is vars statistics number 3. Again, if you didn't do 2 var stats first, your calculator will either give you an error because it won't know what these are, or it will use some other X bar and S of X from a different problem. So you want to be cautious with that. Also, note that I've got the L3 highlighted. This is all the way up here. It's not in the first cell. That'll cause some problems. So I hit enter. I get this. Do the same idea on L4, except it's with Y and Y bar. So this is going to be L4 right here, which is L2 minus Y bar over S of Y. So I'll type that here, L2 minus Y bar divided by S of Y. I've also noticed that some students forget to put that divided by symbol right there. I guess they type the parenthesis and think that's good enough. Of course it's not. Hit enter. Now I should point out that this number here being negative means that the X value is less than the mean of X's, because this is a z-score for the X's. So the X value for this first town is below average, but for this town, it's well above average. Likewise, the Y value here is above average, but on these last 2 towns, the Y value is below average. Now in L5, I'm going to multiply L3 and L4 together. So when I multiply these things, I'll put that in L5. So L5 is L3 times L4. That's the product. So the next part of my formula says to add that up. So I'm going to go to my home screen, and I'm going to sum up. So that second list, math, number 5, sum up L5. And finally, I have to divide that by n minus 1. So I had 5 pairs of data, so I'll divide that by 4. That is correlation, 0.86. Now, what does that mean exactly? Well, that's what we're going to try to figure out on the rest of this lesson. So to shed some light on what this 0.86 means, let's look at some facts about correlation. So the first fact is always graph your data. So you always would like to have a good visual idea of what the data looks like. And when you graph your data, talk about the strength, form, and direction. Strength, form, and direction. Second thing, you can't tell R very well by looking at a graph. Again, R is correlation, and our eyes don't do a great job of differentiating and discerning exactly what R would be or how strong it is. So that's why we use a formula. A good example is those first 2 graphs that I showed you at the beginning of the video. Next, we know that a positive R corresponds to a positive association. So if I have a graph that's increasing, as X gets bigger, Y tends to get bigger, I'll end up with a positive R. If you thought about it being a linear relationship, then the slope will be positive. Correlation, in fact, measures strength and direction of linear relationships. Correlation measures the strength and the direction of a linear relationship. So we talk about height and weight. As height gets bigger, weight tends to get bigger. That's a positive R. As your age in school gets larger, your size of your vocabulary tends to get larger. Positive association. Negative associations have a negative R value. So the more zeros you have, the lower your homework average. That's a negative relationship, a negative association, or a negative R. R values will always be between -1 and 1 inclusive. If the R is +1, that means all the points are perfectly collinear and they have a positive slope. If R is -1, all the points are perfectly collinear and they have a negative slope or a negative association. So the closer the R value is to 1 or -1, the closer the points are to a straight line. Values near zero indicate a weak linear relationship. Now remember, I said that correlation measures strength and direction of linear relationships. So when you're looking at correlation, there's a presumption that the relationship is in fact linear. R kind of answers the question, how linear is it? So if R is zero, a line doesn't do a very good job of explaining that relationship. Now, R uses standardized values. Z-scores have no units. Z-scores have no units. So when I standardize my values to find correlation, I've got no units. So correlation has no units. Furthermore, R won't change when the units change. So let's look back at this formula for a second. If I go through this formula, let's say I'm talking about height and weight. So this is in inches and this is in pounds. So this is inches minus inches, which is inches, divided by inches is no units. Pounds minus pounds is still pounds, but divided by pounds, no units. No units times no units is no units. Added up, no units. Divided by a number minus 1, no units. R has no units. And the correlation doesn't change if the units change. So if I made a graph that had that showed the relationship between height and weight, it doesn't matter if I measure your height in inches or centimeters or miles or hands or cubits. The graph is going to look the same. The correlation is going to be the same. It's just the scale that's going to be different. Correlation measures strength of linear relationships. It doesn't describe curved relationships, even strong curved relationships. So if I look at a graph like this one, it is not linear. But if I talk about correlation, then what I'm saying is, how well do these points match up to some line? And you could see that this line doesn't do a terrible job, but boy, something would do way better than that, namely a curve of some sort. So I may end up with a strong R value even with curved data. Or I may end up with a really close to zero R value. Consider this graph. Data does this. This horizontal line right here might be my line of best fit. But clearly, the relationship is nonlinear. So it's not appropriate to talk about correlation on these two things if I really want to use a curved relationship to describe the data. Correlation is based on the mean and the standard deviation. Now, are the mean and the standard deviation resistant or non-resistant? They're non-resistant. So correlation is non-resistant. The example I gave here, I showed two data sets, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, negative 10. So the points were looking pretty good, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And then I got to 6, negative 10. Without that last point, without that 6, negative 10, correlation's 1. But when I throw that last point in there, look at the correlation. Not only is it way away from 1, it's actually negative now because it was strongly affected by that outlier, because it's based on things that are non-resistant. The next point says that even when I have strong correlation, we don't have causation. And this is a flaw that many people make, or a mistake that they make. Correlation does not imply causation. Just because as X goes up, Y tends to go up, doesn't mean that that relationship is causal. It could be a result of a common response to something else, or perhaps a confounding issue. We'll talk about these things later, But for now, remember, correlation does not imply causation. Just because they both go up together, or when one goes up, the other goes down, doesn't mean that that relationship is a cause and effect relationship. Now examine the formula one more time. What do you think is going to happen if we switch the explanatory and response variables? So instead of putting height here and weight here, I do it the other way around. Or instead of putting college experience here and income here, I switch those. Well, it turns out if I switch my x and y, all I'm doing now is multiplying in a different order, and since multiplication is commutative, the correlation itself won't change. That leads me to my next point. Correlation doesn't make a distinction between explanatory and response variables. It doesn't care which one's which. Correlation doesn't care which one's which. It's the same correlation. Finally, correlation isn't a complete description of the two variable data. If we have two variable data, go ahead and tell us what the mean and the standard deviation are. Those are appropriate things to include in a conversation about correlation. One of the best ways to really understand correlation is to do some examples. Try it. Make a graph of it. Explore it with the formula. See what happens as we go through different problems with the correlation. And that'll really help your understanding of how this formula describes the strength of a relationship.